8.3 talks about testing a claim about the mean. So in the last section we did testing a claim about the proportion. Now we're doing the mean. Hypothesis testing, claim about the mean if the population standard deviation is not known. So if it's known, we use Z. Requirements, the sample is a simple random sample and the value of the population standard deviation is not known. Either or both of the given conditions are satisfied up there. The population is either normally distributed or n is greater than or equal to 30. If that's the case, well, we're going to repeat what we did in the previous section. Recall the logic behind the hypothesis testing, right? H0 says things didn't change. Alternative, things changed. Either they're less than they used to be, more than they used to be, or they're not the same anymore. If we take a sample and find the point approximation, a product estimate is if x bar equal 10, which is the mean, then we do not reject, fail to reject the null hypothesis. If the average, if the mean is greater than 10, then we do not reject the null hypothesis. If the mean is less than 10 by a little, then we do not reject. And if the mean is less than by a lot, then we reject. Now, how do we decide if it's a lot or not? So if we're testing, the null hypothesis says the average didn't change. The alternative says the average is less than. So if it's greater than, then that means, well, the alternative wasn't really correct. If it's less than by just a bit, then we say, well, it's about the same. But if it's less by a lot, then we say, you know what, this is correct. Now, what's a lot? Well, that's where the test statistics comes in. Either you figure out a probability. If the probability is less than 5%, we say, well, you know, that's not normal for us to accept this. That means 95% support that. And if we do a test statistics, we figure out a rejection region based on the 5% and we go from there. So the same as before. Steps for a hypothesis test when applying to test the population mean. And I'm going to go over what we went over last time. It's the same idea. So we want, it is a valid, we want it to be a, I was going to say a simple sample, simple random sample. Requirements 2 and 3 above have to be satisfied. Hypothesis testing, well, it's one of three things. If the null says it's the same, it always says it's the same. Either the average, either the alternative will say, well, it should be less than, depending on a sample, or it's greater than, or it's not equal. And we know that not equal is a two-sided, so we take 2 times the probability. Level of significance, if not given, if they don't specify, in most problems they specify. If not given, we use 5% as a guiding principle. If they want to change that, they have to tell us that. Test statistics, well, chi-squared, that's coming up in the later chapters. We use a z-score if the population standard deviation is given. It's not in this case. We're going to use a t-score. The test statistics is the sample minus the population divided by S over the square root of n. And that's how it's going to work. So, find a critical value or a p-value and check using either the critical value or the p-value, either way. So either you reject the null hypothesis or you fail to reject the null hypothesis. And if you remember, you have to really identify where the claim is so you would know how that works. So if I'm doing a single-sided, I figure out what's the probability that area to the left of this, that's the p-value, right? And that's the test statistics right there. And figure out the probability. Well, if it's less than 5% or more than 5%, right? Less than 5%, I will reject the null hypothesis. More than 5%, I will fail to reject. If we're dealing with a two-sided, right, then we do alpha over 2, and we take twice the p-value, and the same conclusion as before. And the right side, we're figuring out the probability that the test statistics is greater than, right? And we would reject the null hypothesis if it's less 5% or bigger than, unless they change that, unless they tell us, well, now go 10%, now go 7%. Test statistics, we figure out the rejection region, and we see if the test statistics fall in there. That's a critical value method. If it falls in there, we reject the null hypothesis. If it falls in there, we fail to reject. Same thing here, and same thing here. And that's how this works. Here we fail to reject. Always the null hypothesis. And here we reject. And the same deal with the other ones. We will start with our first example. Kaiser Foundation Hospital claims, this is the claim, that the mean waiting time for patients to be seen in the emergency room is 20 minutes. So they claim the null hypothesis is that the mean is 20 minutes. And the claim is right there. You need to know that to know whether to support the claim or not, because we accept or fail to accept the null hypothesis. The alternative, let's see what happens. If a random sample of 40 patients produced a mean of 18.5. So the claiming is 20 minutes. We took a sample of 40 and we got it to be 18.5 minutes. So it's less than, but let's see what they want. And a standard deviation, the 40 produced a standard deviation of 4 minutes. So that's not the population. I can use the z-table. And here they changed alpha. Here they want us to be only 10%, a 90% confident level to test the claim that the mean wait time is equal to 20 minutes. So the wait time is equal to 20 minutes. Now, the alternative, they didn't specify what they want. Since the claim is with the null, we say the alternative, let's say this is other than 20 minutes. Not equal to 20 minutes. So, in this case, and if you decided to use, since the average turns out to be less, if you decided to use less than, I'll accept that as well. Since they didn't specify, we say not equal, but it could be less than, and I really wanted to do an example on each. So, our examples, one of them is less than, one of them is greater than, I wanted to do not equal. So if you use less than because this is less than the 20, I'll accept that. That's not a problem. Because they didn't specify, it's up to you. Either use less than or not equal. I'm going to use not equal for practice purposes. And we're going to work with the test statistics. What's the test statistics? Test statistics is the t-distribution. That's x bar minus the population divided by s over square root of n. And that would be 18.5 minus 20 divided by 4 over the square root of 40. And that would be, and there it is, 18.5 minus 20 divided by, and we know that's, 4 divided exactly as you see it. This calculator could keep track of that. Close parentheses, negative 2.372. Negative 2.372. I want to copy that for you in the notes so you can see it in case you look back at these notes. You know how we're getting all of these values. It takes a bit longer, but it's okay. There it is. Okay, well now let's do both of those. P-value or test statistics. And I'm going to start actually doing the p-value with a graph so we could see it better. So the p-value, this is the left side. The p-value, well, we're going to figure out what's the probability that t is. And again, remember, we got it to be less than. This is 0, So negative 2.372, you're trying to figure out what's the chances of that happening. Less than negative 2.372. And how do we do that? Well, we use our calculator. And if I use my second distribution, let me enlarge that just a bit. Okay, maybe that. A distribution. We want the what do you call it? T distribution. T distribution. Not binomial. Oh, did I miss it? T distribution. Let's go to one again. Oh, it's right there. Missed it. TCDF. So the TCDF, the lower end is negative 1. That's true. The upper end is negative 2.372. Degrees of freedom, they said n equal 40 to 39, if you remember. Paste and give me that probability, and there it is. Now, we're going to always find the probability. You need to know what that means. The work is almost identical all the time if you really pay attention. So I found a probability. Do you know what that means? This probability happens to be I'm sorry. I decided to do this problem on, I forgot. We would have done it. That's how you do it on one side, right? But we're trying to do it on two sides. Doesn't that mean that you multiply this by 2? 2 times 1.14% is really 2.2%. So the chances of that happening is 2%. Well, we reject the null hypothesis. Do you see that? They gave us 10. How about here? Well, if we want to do it using the critical region, and you need to know both. So this is how we're going to do it using the critical region. We're going to say, well, look, alpha is 10%. If it's two-sided, we want both of those to be 10%. That means 5% each. Or simply, this is 90%. Right? Now, if I'm using a t-distribution, I have to use to the left of a number. That's how it works. So I have to use 0.005. I have no choice. I would go second distribution, inverse t-distribution. The area to the left is 0.95. Degrees of freedom are 39. And tell me what that cutoff is. 1.68 and negative 1.68. If you were doing a single-sided, that would have been 90%. So, and that's coming up. So if I look at the test statistics, the test statistics is right there. We already found it. It's negative 2.372. Rejection region is right there and right there. Isn't negative 2.3 to the left of negative 1.68? So we reject the null hypothesis. Both of those should yield the same conclusion. So you reject the null hypothesis. What does that mean? That means there is not enough sample significant, it needs the thinner, significant evidence to support the claim that the true mean waiting time, and I'm just reiterating what they said, for patients to be seen in the ER of Kaiser is not equal to 20 minutes. It's less, it's better, but we're testing whether it is or not. Again, let me remind you what I remember. Type 1 always, that's when we reject the null hypothesis, and since it's an error when it was true. So here you would conclude that the wait time is other than 20 minutes when in reality it is. And type 2 error is when you fail to reject, so you kind of support it when it was false. And that means your conclusion that the wait time is not other than 20 minutes when in reality